So the first thing I want to talk about when we talk about natural logarithmic functions when we are doing differentiation and integration is I want to talk about the problem you run into with this power rule. So if we're doing integration, right, antiderivative of a power, you take the power, right, and you add 1 to it, and that's your new power, and then you divide by that power. And that's all well and good until we run into something like this. So I would rewrite this guy, right? And how would I rewrite him? X to the what? And my rule says to add 1 and divide. What's my problem?
You'll get a 0.
You'll get a 0. And so all of a sudden we run into a function that it doesn't work for. The power rule doesn't work for. And there's a reason it doesn't work for. And the reason that it doesn't work for that is because this actually gives you a logarithm. The antiderivative of something over a power, like to the -1, is the natural log. Meaning that if I were to take the derivative of natural log, I would get 1 over that guy. And that's actually where they get it from. They get it from the graph of it, which we're going to look at in a minute. So the first thing you want to memorize is, if I have 1 over something to the power of 1, it is going to be a natural log of that. So the ln of x here, the natural log of x, derives to 1 over x, meaning 1 over x derives to the natural log. Antiderivative is the natural log of x. And so the antiderivative of this guy, assuming that I plug in an x here, is going to be the natural log of it. The domain is a set of all positive real numbers. Why would it be positive real numbers? Because it is a natural log, and we're going to look at the function itself. The function actually does not go below. And if you'll recall, when we do logarithms, you can't take something to a negative power, right, and get it to a negative number, right? And so you're going to have the positive real numbers because we're talking about a positive number we start with. Natural log, my base is e, 2.17. There's nothing I can take e to that will take it to a negative number. So we have to do positive numbers here. If you put in a negative, it's going to give you an error. So here's my graph of ln of x. It looks like this guy right here. You'll notice that it gets infinitely close, but it doesn't go into the negative region here. I can see about what's happening. So think about what first derivative tells me. First derivative tells me the slope of the tangent line, right? So if this is my function, the slope of the tangent line, what they actually started finding is it's 1 over wherever I am. So let's say I'm at 2. The slope of this line is going to be 1/2. And so then the derivative there would have to be 1/2, which means the antiderivative of 1/2 would have to be ln of 2. Okay, and so from this is where they got slope of the tangent line is kind of where we got our, well, the antiderivative of 1 over x must be ln of that number, natural log of that number. So then we review a little bit of things about logarithms that y'all are going to love doing because you'll remember it. The first are just the properties. The domain is 0 to positive infinity, and the range is negative infinity to positive infinity. So your y can be anything, but your x's have to be 0 to infinity. They have to be positive. The function is continuous, increasing, and 1-to-1. Obviously, by the word function, we know it's 1-to-1, but it is continuous and increasing. The graph is concave down, all right, which we just saw. Logarithmic properties. The ln of 1, or log of any base of 1, is 0, because anything to the 0 power is 1. These are my expansion rules, which hopefully you remember because we've done them twice. I think we did them in Algebra 2 and in Pre-Cal. If you're multiplying two things within your natural log, you can expand it by addition. If you take it to a power, you can bring the power in front. And if you're dividing, you can expand by subtraction. We're going to use this with derivatives because we're going to either expand or contract to use the derivatives of these guys. So make sure you know those properties. So example 1 just has us expanding these things, not actually taking the log of these, just expanding them. The first one is division. And so if you'll recall, we would expand this with subtraction. We would say ln of 10 minus ln of 9. B, that is actually something to a power, right? You can actually rewrite 3x plus 2 to the 1/2, right? And so my expansion rules say that I can bring that 1/2 in front and do the ln of 3x plus 2. The next one is a multiple ones, multiplication and division. And so if I were to do that division first, I would say ln of 6x minus ln of 5. And then I can expand this guy even further. And I can say ln of 6 plus ln of x minus the ln of 5. All right. The last one gives me lots of them. I'm going to use my division first. I would say the ln of x squared plus 3 to the second power minus the ln of x cubed root of x squared plus 1. I can expand further. For this first one, I can bring this in front. So 2 ln of x squared plus 3. This second one, I can expand that multiplication, ln of x plus, and I can expand this to the 1/3 power, 1/3 ln of x squared plus 1. You do want to do this, because that whole thing was on bottom. And so what happens when you expand completely, you distribute that negative, minus ln of x minus 1/3 ln of x squared plus 1. If you leave that plus there, your order of operations will kick in, and it'll look like that whole thing was multiplied by it, not just the denominator. So E is, they give you the approximation of it, 2.718, and it goes on forever. Don't bother memorizing it. If you go that far out, just use your calculator. People usually round it to 2.17, just like with pi, 3.14. It is the natural number here. It is what E represents. They do point out the obvious here, but the natural log of E is just 1. All right, meaning if I had 1 over some variable and my top number here was E, I'm just going to get 1 when I do all that work, because it's going to be the natural log of E, which gives me 1. Evaluating. If you're evaluating your calculator, you're literally just going to plug it in, right? Natural log is the ln. It should be inversely on your calculator to the e to the power. And then your log is base 10, which should be inverse to your 10 to the power buttons, which you literally just plug it in to evaluate it. Again, not the hard part of natural logs. Derivatives. Now, let's talk about derivatives. If the antiderivative of something over x is ln of x, then the derivative of ln of x is 1 over x. That's simple. What happens when you have a function in there, though? When you have a function, you have to consider the derivative of the function itself. And so if this x is no longer an x, but is, say, an x squared, or some function, any function, you have to consider the derivative of the function as well as putting it in the denominator. So if I have the natural log of x and I'm taking the derivative, it's just going to be 1 over x. But if I have the natural log of a function, I have to take the derivative of the function, that is my numerator, and that is over the original function, that is my denominator. All right? So let's look at these examples. They want the derivative of the natural log of 2x. This is a function other than x, right? So I have to do the derivative of 2x. That's my numerator. What is the derivative of 2x? It's just 2. And then the denominator is going to be just my original function, 2x. And yes, I would reduce that. What does that reduce to? 1 over x. And that is my answer. That is my first derivative, 1 over x. Let's look at the second one, b. Derivative of the natural log of x squared plus 1. What's my derivative of x squared plus 1? 2x. And remember, my 1 goes away, turns to 0. I put that over my original function, x squared plus 1. I cannot simplify that anymore, so that is my answer. I use multiple rules for C and D, okay? I'm not just doing my natural log rule. If I'm going to look at C, I have to notice that it is x times the natural log of x right here. So I must use my product rule. I must use my product rule. the derivative of the first being x. So the derivative of first is just 1, times the second, that is just ln of x. Then I'm going to add to that the first one, x, times the derivative of the second. Well, the derivative of ln of x is just 1 over x. And then I'm going to simplify it. 1 times ln of x, that's just ln of x. X times 1 over x, that is just 1. And that would be my derivative using the product rule. The last one uses the chain rule. The chain rule, derivative of the outside times the derivative of the inside. So for the chain rule here, your outside is your ln of x grouped to the third power. So we're going to do the derivative of the outside, that 3 times the ln of x squared. And then we're going to multiply it by the derivative of the inside, the ln of x. What is the derivative of ln of x? Just what? 1 over x. So I end up, to simplify it a little bit there, which they didn't, but I would do it this way. I would say 3 ln of x squared all over x. And either one of those is fine. This is kind of hideous, right? I don't want to take the derivative and then do the chain rule and all that junk as my numerator necessarily. And so there's a little bit easier way to do this. I am going to go back to my expansion rules and I'm going to say, well, the natural log of the square root is the same thing as x plus 1 to the 1/2, right? I can expand that, can't I? My rules say I can. My rules of expansion tell me I can take this exponent and put it in front. And it's just a coefficient, which doesn't require a special rule. So 1/2 ln of x plus 1. If I have a coefficient of a function and I'm taking the derivative, I just put them in front, right? So I would just say 1/2 times this derivative. Well, this derivative is the derivative of this guy. What is the derivative of that? 1 over the whole thing, x plus 1. So that's 1 over 2, x plus 1. And that is my answer. Expand it, just expand it. We're going to look at each one individually. So I'm going to look at my x. I'm going to look at my x squared plus 1 squared. And I'm going to look at my square root of 2x cubed minus 1. And I'm going to expand it. So I have the natural log of x. It's being multiplied by this guy right here, right? I can expand him, can't I? I can put the 2 in front, ln of x squared plus 1, right? Divided by this guy right here. I can expand it. Division means subtract. It's to the 1/2 power. That 1/2 can go in front. ln of 2x cubed minus 1. There we go. And then I can just take the derivatives individually. And they are much more simple this way. The derivative of ln of x is 1 over x. Plus, I'm just going to say 2. The derivative of this guy is just the inside. That's 2x, right? Over the actual function itself. Minus 1/2. Derivative of the inside. That is 6x squared over the whole function. And then I'm just going to simplify it. 1 over x plus 4x over x squared plus 1. These guys will reduce. Minus 3x squared. Oh, no, those guys won't reduce. Ignore me. Not that one. We're going to reduce it with this one. 2 over 2x cubed minus 1. That would be my derivative. So here's one that does not have a natural log in it. So if I were to just come upon this, I would say, oh, I'm going to have to do the chain rule and the quotient rule and simplify and blah, blah, right? And which is true. You could do that. You could also use implicit differentiation here. By that I mean, think back to when we first learned logarithms. And when you came upon an equation that didn't have a log, but expansion would help you, you just took the log of both sides. And when you take the log of both sides, all of a sudden you can use expansion. And then you can end up solving. All right, and that's what we're going to do here. We're actually going to take this and we're going to do the log of both sides here. So we're going to say the natural log of y equals the natural log of this crazy thing that they gave us here. And then all of a sudden, we now have something we can do. Now to do this one, we have to take the derivative of both sides. So that means we have to take the derivative of y. We're just going to write that, think about implicit differentiation, as y prime. And we're going to put that over just our function, which was y. Y prime over y. On the right-hand side, we're going to have to expand first. And so I'm going to expand up here, and then we'll do the derivatives. So we'll expand this guy. We're going to bring that 2 in front, because it's an exponent. Natural log of x minus 2. That's the numerator. Subtract the denominator. The exponent on the denominator is 1/2. So bring that in front. And then natural log of x squared plus 1. And now we can take these derivatives. And that should equal the derivative of the right-hand side. Okay? So the derivative of this, we do the derivative of the inside. That's just 1. So we have 2 times 1 over my inside, which is x minus 2. Minus, we have the 1/2 times derivative of the inside is 2x over the x squared plus 1. And I want to simplify these as much as possible. And then I'm going to multiply across. So for this, I'm just going to put my 2 on top there. For this, I'm going to cancel those 2's. Cancel, cross cancel. So I just have x over x squared plus 1. Now when we're solving for the derivative of y, that's y prime. So I need to get y prime by itself. How do I get y prime by itself? I have to multiply by y, which means I have to multiply this whole thing by y. All right? And here's where you're just using your algebra skills, which hopefully you still have. All right? So I'm going to use substitution here. I'm going to substitute this y for what I know y is. Right here, right? This is y. I'm going to plug it in. So I am going to say then that x minus 2 squared over, I'm going to write it x squared plus 1 to the 1/2 multiplied by 2 over x minus 2 minus x over x squared plus 1. Now you don't want to leave it this way. This is not pretty, okay? What I want to do here is I want to get a common denominator between what's on the inside and simplify that a little bit. And then I can see if anything will cancel if I can multiply through. And I may not be able to, but we shall see. So we're going to look at what my common denominator is, all right? What is my common denominator between these two? Don't overthink it.
How did you get from the very middle?
I just replaced my y with what I know y is.
Oh.
Yeah. No, it's x minus 2, x squared plus 1. It's these two. So you're going to just use like your butterfly method or whatever, your cross multiplication, whatever you have to do. Your entire denominator here is going to be x minus 2 x squared plus 1. All right, and we still have this on the outside, so we still have the x minus 2 squared over the x squared plus 1 to the 1/2. That's out here on the outside, all right? Right? On the inside here, I just multiply, right? I'm missing my 2. So this becomes 2x squared plus 2. I just multiply that, right? And for my x, I'm missing my x minus 2. So that becomes x squared minus 2x. Yes? I'm just getting a common denominator. I multiply this one by this guy. That's what I'm missing. So that's 2x squared plus 2. I multiply this one by this guy because that's what I'm missing there. X squared minus 2x. Then I'm just going to simplify these right here because it's subtraction. So this is subtraction. All right. So I have 2x squared minus x squared gives me what? 2x squared minus x squared gives me x squared. The only x that I have is this negative 2x, but it's minus. So minus a negative 2x gives me plus 2x, right? And then the 2 also cannot combine, so I have plus 2. And then I'm going to look and see if I can simplify anything between those multiplications, all right? Up here in the numerator, I have x minus 2 to the second power. Down here in the denominator, I have x minus 2. I can cancel one of those, right? I'm just multiplying. Think about when we were simplifying rational polynomials, right? Cancel one of those with one of those, right? And then these two are the same base, right? What do I do with variables with the same base? X cubed times x squared is x to the 5th. We add their exponents. The exponent here is 1/2. The exponent here is 1. 1/2 plus 2/2 is 3/2. So in the numerator, I have just the x minus 2 and the x squared plus 2x plus 2. And in the denominator, I have x squared plus 1 to the 3/2. For your natural logs, absolute value doesn't really make a huge difference. The reason is your domain is all positive numbers. If my domain was not all positive numbers for this function, then we would have to consider the positive and negative. But for your natural log, your domain is all positive numbers. So it doesn't make a difference. They go straight into a trig function though, which is just as easy as all the other ones. They want me to find the derivative of natural log of cosine of x. Well, I'm just going to take the derivative of the cosine. What is the derivative of cosine? Negative sine of x. And I'm going to put that over the function that I started with, cosine. So I have the negative sine of x over the cosine of x. I do not want to leave it this way. Why? It's like leaving a fraction as 2/4 here. You would never do that. And so you definitely want to simplify this. Leave your negative there, but it is the negative tangent of x. When they want the relative extrema on this, they want the max and min, potential max and mins here. And so you have to take the derivative and then you have to set the derivative equal to what to find your max or min? 0. And so that's what we're going to do. Our derivative then here is the derivative of the inside first. That's our numerator, which is going to be what? What's the derivative of that? 2x plus 2. And we're going to put that over the whole function. All right. So then you're going to set it equal to 0. Where is this function 0? Where does it equal 0? We're not talking about where it's undefined. We're talking about where it equals 0. How do we know where it equals 0? Yeah, our numerator. 0 divided by anything is 0. So we're just going to set my numerator equal to 0. We're going to get x equals -1. If I want the actual negative extrema here, I need to plug it in. It doesn't make me identify whether it's max or min, but it does make me plug it in because I need my y value, okay? So if my x value is -1, I have to plug this in here for my y value. So I'm going to say, to find my y, it's going to be the natural log of -1 squared plus 2 times -1 plus 3. Right? Make sense? So a natural log of 2 would be my x value here, which is a hideous answer, but you could round it if you wanted to. And you look at the graph that they gave you, and you can see that it is a minimum. If they wanted you to identify it, is this a max or min? You can do your interval test. Well, we can go from -infinity, right, to -1, and then from -1 to infinity. And we can plug those in. And so if I took like a -2 and plugged it in up there,